Good morning, students. As we started the group number 16, some basic things about the group number 16, that is its atomic and physical properties. So now next we started the chemical properties. Before discussing the reactions of group number 16 element, first of all focus on their oxidation states. In which oxidation state they form the stable compound. So here, as the general electronic configuration for group number 16 element is NS2NP4, isn't it? So here are the two possibilities. First one, to gain 2 electrons, and second one, to lose 6 electrons. It means they have the tendency to gain as well as lose the electrons. Hence, they show negative as well as positive oxidation state. So for negative oxidation state, oxygen show two type of negative oxidation state, that is -2 and -1. If we discuss about this -1, then it is in the peroxides, that is O2 2 negative. This -2 charge is on both the oxygen atom. So if you divided this charge in both the oxygen atom, then each oxygen carry -1 charge. This ion is called as peroxide ion, and this -2, it is in its simple oxides. Simple oxides, which means oxygen alone carry -2 charge, isn't it? Now next one about sulfur, selenium, tellurium. They have the tendency, but this tendency is very rare, to show -2 oxidation state. Why? Because as we move down the group, that is oxygen, sulfur, selenium, tellurium, polonium, then electronegativity decreases. It means tendency to attract the electrons, to gain the electron, that is decreases. Hence, to show the -2 oxidation state in their compounds, it is very difficult for these elements. Next, in case of polonium, as it is least electronegative, it never show -2 oxidation state. So this one is the stable oxidation state only in the case of oxygen, and little bit in the case of sulfur, selenium and tellurium. Polonium do not form any compound in -2 oxidation state. So let us now discuss the positive oxidation states. So these elements shows +2, +4 and +6 oxidation state. Here, in case of oxygen, it shows +2 oxidation state as well as one more, that is +1 oxidation state. As only one element, that is fluorine, is more electronegative than oxygen, it shows this positive oxidation state only with fluorine. This +2 oxidation state in case of OF2, and this +1, it is in case of O2F2. These are not called as oxides, they are called as fluorides, as fluorine is more electronegative than oxygen, isn't it? So it is called as oxygen difluoride, and it is dioxygen difluoride. Now other element shows +2, +4 and +6 oxidation state. Why they show these oxidation state, that is of +4 and +6, but oxygen do not? Because as they have presence of vacant d orbitals. Due to the presence of these d orbitals, electrons from lower energy orbitals promoted to the higher energy orbitals to make desired number of half-filled atomic orbitals. For example, if we discuss this in case of oxygen, then its electronic configuration in valence shell, which is second, it has 2 electron in 2s and 4 electron in 2b subshell. As second shell do not have d orbitals, so oxygen have the tendency to form 2 covalent bond, isn't it? 4 and 6 bonds are not possible in case of oxygen, as it do not have d orbitals. But if we discuss about sulfur, its valence shell is third, so it has 2 electron in 3s orbital, it has 4 electron in 2p orbitals, 3p orbitals, and here the 3d orbitals are empty. So for 2 bond, here are the 2 half-filled atomic orbitals present on sulfur in ground state, but if we see its compounds in which sulfur is bonded with 4 atoms, for example SF4, then it must have 4 half-filled atomic orbitals. How it happen? The 1 electron from lower energy atomic orbital promoted to higher energy atomic orbital to make 4 half-filled like this. This is now 1 and 1 electron from 3p jump into 3d. Now sulfur have the tendency to form 4 bonds, but if we discuss about SF6, so it form 6 bonds. For this, sulfur must have 6 half-filled atomic orbitals. So now one more electron promoted, that is from 3s, this one 3s to 3d, to make 6 half-filled atomic orbital. Now 1, 2, 3, 4, 5, 6. In this case, sulfur has the tendency to form 6 bond, isn't it? So for oxygen, only +2 oxidation state exists. +4 and +6 oxidation state do not shown by oxygen. Why? Due to the absence of d orbitals. But in case of sulfur, selenium, tellurium, polonium, they may show +4 and +6 oxidation state as they have d orbitals. So now if we move down the group, then tendency to show +4 oxidation state increases and tendency to show +6 oxidation state decreases. The reason is inert pair effect. As we move down the group, nuclear charge increases, which attract the s electrons of valence shell with more power, so make them not involving in the bonding phenomena. This effect is called as inert pair effect. So in case of polonium, it only shows +4 oxidation state. It do not show +6 oxidation state. Okay. Now if we discuss the compounds of sulfur, selenium, tellurium, polonium with oxygen, then they show positive oxidation state, and oxygen it shows negative oxidation state of -2, isn't it? So here they shows +4 oxidation state. Now their compound, for example sulfur with oxygen, that is SO2. So in case of SO2, sulfur having +4 oxidation state, it means this oxidation state decreases up to +2 or 0, isn't it? This oxidation state increases up to maximum is +6. Decrease in oxidation state, that is called as reduction. So here these oxides behave as oxidizing agents. When their oxidation state decreases, then they behave as oxidizing agent, and when their oxidation state increases, then they behave as reducing agents. So these compounds behave as both. It means their compound, sulfur, selenium, tellurium, polonium compounds in +4 oxidation state, they behave as both agents, oxidizing agent and reducing agent. If we discuss about its +6 oxidation state, so they form compounds in +6 oxidation state with only fluorine, as it is the most electronegative and a smaller size atom. Here they only behave as +6 is the highest oxidation state, so here only decrease in oxidation takes place, and decrease in oxidation state is reduction, and the agent is oxidizing agent. So in +6 oxidation state they behave as oxidizing agent, but in case of +4 oxidation state they behave as both oxidizing as well as reducing agent. Is it clear? Next one, if we discuss about the order of chemical reactivity chemical reactivity of group number 16 element, then it becomes oxygen is the most reactive element of group number 16. Then reactivity decreases as they have the tendency more to accept two electrons, and this tendency decreases as we move from top to bottom in the group. Hence chemical reactivity also decreases as we move down the group. Next, one more point here is to discuss about the multiple bonding. So in case of multiple bonding, oxygen have the tendency to form p-pi multiple bond region due to its smaller size and high electronegativity. And as we move top to bottom in the group, size increases, electronegativity decreases, hence tendency to form p-pi multiple bond decreases. Other elements they have the tendency to form p-pi d-pi multiple bond. As they have d orbitals, they form p-pi d-pi multiple bond, which is not possible in case of oxygen, isn't it? But this tendency to form p-pi d-pi multiple bond down the group decreases as the size of element, that is central atom, increases. The size of element increases means the size of their orbitals increases. Hence overlapping is not so much effective, which results in the less stability of p-pi d-pi multiple bond. So this p-pi d-pi multiple bond, it is stronger in case of sulfur, isn't it? So now next point is the reaction of group number 16 elements with hydrogen. As hydrogen is more electropositive than these elements, they shows negative oxidation state with hydrogen. So they form hydride having formula, general formula H2E. Here E is either oxygen, sulfur, tellurium, selenium, tellurium or polonium. Now if we discuss their preparation, so they are prepared by, it is the simple method for the preparation of these hydrides, that they are prepared by the action of acid on metal sulfide. As other are selenides, tellurides, etc. For example, if we have FeS, iron sulfide, and when suppose it react with HCl, so now here it form FeCl2 plus H2O and H2S. There two oxides are formed. One is H2O and second one is hydroxide H2S. So this one is the preparation. By the action of acid on the metal sulfide, either on metal selenide and either with metal telluride. Okay, H2O is formed in all the reaction. If you taken here sulfide, then H2S is formed. If you taken here selenide, then H2SE is formed. If you taken here telluride, then it become H2TE. Okay, now next one is structure. So their structure is, it become V shape with sp3 hybridization. How? Here with sp3 the symmetrical form is tetrahedral, but that tetrahedral is only in case of when all our electron pairs are the bond pairs. But here if we see, then element central atom having lone pair, so its geometry is not symmetrical but it is unsymmetrical. For example, if we discuss about water H2O, here the central atom is oxygen. Here oxygen is bonded with two hydrogen, that is covalently bonded with two hydrogen. So first of all, write its electronic configuration, that is 1s2, 2s2 and 2p4, expanded 2px2, 2py1 and 2pz1. Now this undergo hybridization, in which 1s and 3p orbitals involved to give 4 hybrid orbitals. These hybrid orbitals are called as sp3 hybrid orbitals. Okay. Electron distribution is the same as in case of atomic orbital, one having 2 electron, second also having 2 electron and remaining having 1 electron each. Okay, out of these 4 sp3 hybrid orbital, these two half-filled hybrid orbitals, they overlap with 1s of hydrogen atom. It also overlap with 1s of hydrogen atom, and they are remaining on oxygen as lone pair. So the structure is this one. This is oxygen that is bonded with 2 hydrogen and 2 lone pair are present at oxygen. In case of water, this angle is 104 degree 5 minute, which is not tetrahedral angle. It is less than the tetrahedral angle. Why it is less? Due to the presence of these lone pair, repulsion between lone pair bond pair is more, which results in the bending of these bond pair in downward direction, hence angle decreases. Now if we discuss about the angle of these hydrides, sulfur, selenium, tellurium and polonium, then angle value of bond angle decreases. Why it decreases? Reason. What is the reason for this decrease in angle? The highest angle is shown by water and the least one is shown by H2TE. Reason, as the size of central atom increases as we move down the group, size of central atom increases, the bond pair lie away from central atom, hence results in less repulsion between them, which decreases the bond angle. So what is the reason in decrease in the bond angle of these hydrides? That is the less repulsion between bond pair and bond pair as they move away from the central metal atom. So as its size start to increase, what happen? Then bond pair lie away from central atom, which results in decrease in bond angle. So this one is the structure of hydrides of group number 16. Next one, we discuss about their properties. So they are the same as we discussed the properties of hydrides of group number 15. So first one about the physical state. So generally they are present in liquid state. Mostly if we discuss about hydride of oxygen, and other they are in gaseous state. Hydride of oxygen, it is colorless, it is tasteless, non-poisonous. It is not poisonous, but other they have unpleasant smell and they are poisonous. These are the poisonous gases. Now next property, very important property, that is volatile behavior. So this volatility, it is from H2O to H2S. Volatility increases, and after H2S to H2PO it decreases. Why this so? That first volatility increases, then it increases as that it depend upon the interaction of the molecules. H2O having the hydrogen bonding, isn't it? And other van der Waal interaction. So what is the result? As we move from H2O to H2S, water to hydrogen sulfide, here the interaction are weak than the water, so easy to cleave that interaction. It means H2S easily vaporize, hence its volatility is more than H2O. But as we move further down the group, size of the central atom increases, which increase in the van der Waal interaction. Hence, if interaction are strong, then require more temperature to cleave that interaction. Hence, volatility decreases. Other reason why it increase, because boiling point decreases. And why here it decrease? Because boiling point increases. Okay. Next point is acidic character, means to say release of H positive ion, and this release of H positive ion depend upon the bond strength. And as we move from water to hydrogen sulfide, selenide, telluride and polyamide, the size of central atom increases, which results in the weakening of bond. Hence, easy to cleave that bond, easy to release H positive ion. So, down the group, their hydrides acidic behavior increases. Next property is thermal stability. Thermal stability. So as we move down the group, size of central atom increases. Again, it is explained in terms of bond strength. So the bond strength decreases. Hence, it is opposite. Hence, thermal stability decreases. That is, hydrogen polyamide, it is less thermal stable. Water is more thermal stable. Next one is reducing character. Reduction. Reduction means to say to provide hydrogen to other, or we also here can say reduction character is the capacity to reduce. It means decrease in oxidation state, and in case of polonium, lower oxidation state is more stable. So if we see the reducing character, then it is same as that of acidic behavior. As we move down the group, size increases, bond strength decreases, easy to release hydrogen again, hence reducing character also increases. So again, acidic character down the group increases, thermal stability down the group decreases, and reducing character down the group increases. So this is the reaction with hydrogen of group number 16. And that's it.